Hello everyone. I hope all of you are doing well in these tough times. I'm Swatilekha and I'm here to deliver my lecture on design of footing. Proceeding further, the two important things that you must remember about footing is that footing helps in transferring the load of superstructure to the soil. And the next thing is that it may rest on soil directly or may transfer the load through pipes. See, the basic fact is load bearing capacity of masonry or concrete walls and columns is much higher than that of the soil. Hence, they cannot be rest directly on the soil. So, load from the superstructure is to be spread to a wider area so that the load on soil is within the safe bearing capacity of the soil. Now, here comes the role of the footing, which is spreading the load over a wider area. Now, if the footing may be of masonry, plain concrete, or RCC concrete, and uh, if it is the case of plain concrete, then the dispersion angle of the load is 45 degree as shown in this figure. The next thing is, what are the different types of RCC footings? One of them is one-way reinforced footing and the second one is two-way reinforced footing. Now, one-way reinforced footing are basically meant for the walls. It may be a masonry wall footing or it may be a concrete wall footing. If it is a masonry wall footing, then it may be designed as a cantilever of span having a length L is equals to B by 2 minus BW by 4. Now, what is B? Capital B is the entire width of the footing and BW is nothing but the width of the column. And if it is a concrete wall footing, it may be designed as a cantilever of span length L is equals to B by 2, capital B by 2 minus BW by 2, where again capital B is the width of the footing and BW is the width of the column. Next comes the two-way reinforced footing, which are basically for the RCC columns. There are three types of two-way reinforced footing. One is the isolated column footing, the combined footings, and the raft footings. Instead of going into the details of these kind of footings, as you've already studied them earlier, I will be focusing on the design of isolated column footing. Now, depth of the isolated column footing, the minimum depth of the footing is calculated by Rankine's formula, which is given by H is equals to P by W into 1 minus sine alpha upon 1 plus sine alpha, where H is the minimum depth, P is the safe bearing capacity of the soil, W is the unit weight of the soil, and alpha is nothing but the angle of friction of the soil. And the cover that you have to consider is either 50 mm or 75 mm. 50 mm for a plain concrete bed and for others it is 75 mm minimum cover. The minimum thickness as per the IES 456 is prescribed as 150 mm for the footings that are resting on soil and 300 mm for the footings resting on piles. And the minimum reinforcement will be minimum dia of the bar that can be used is 10 mm dia. The two important things that you need to focus is thickness required at the edges of the footing is 0. So at free edge, the bending moment and shear force is considered to be 0. And the minimum reinforcement for the slab and beams are applicable for footings as well. Moving forward, the next thing is load for the foundation. The load to be used to determine the size of the footing should be based on the serviceability conditions and not on the limit state of collapse conditions. That is, basically, the limit state of collapse deals with the safety of the structure, and limit state of serviceability deals with the durability of the structure. So, whatever load you are going to use will be based on the serviceability criteria instead of the collapse conditions. Now, these three are the load combinations used for foundations. First is the combination of dead load and imposed load. Second is dead load and wind load. And the third one is the combination of dead, wind, and imposed load. As far as the self-weight of the footing is concerned, it can be used as 10% of the load from the column that is being transferred on the footing. And this load will be finally, this 10% load of the self-weight plus the load being transferred to the footing will be used for determining the area of the footing. Again, there are two important notes. The self-weight directly gets transferred to the soil without creating any bending moment or shear force on the footing. And in case of multi-story buildings, allowable reduction in the live load is advantageous. Let's see what are the various design steps for isolated column footing. First of all, before going to the design steps, let me tell you that there are basically three kinds of isolated footings. One is the square footing, the rectangular footing, and the circular footing. Now, isolated footing may be of uniform thickness or it may have sloping top. Today, in this lecture, we are going to design isolated square column footing. Now, the first step is size of the footing. As I have already said, that the load on the soil is capital P plus P by 10, where P is nothing but the axial load transferred to the column. Okay, and as I said, that 10% of this load will be considered as the self weight. So the total load is P plus P by 10 or 1.1 times of P. Therefore, the area of the footing required will be 1.1 times of P, that is the load on the soil, divided by the safe bearing capacity of the soil. As far as the safe bearing capacity of the soil, mostly you will be given the safe bearing capacity in the question. The next is what will be the size of footing. Now, since we have the area of the footing, we can easily calculate the size of the footing. This because of the basic fact that we are studying the square footing. So it will be obviously under root of A. And whatever value you are going to get after this, you have to round it off to the next higher multiple of 100 mm size. The next step is determine the soil pressure for the factored load. See, action and reaction. These are the two important things. Action is the load that is being transferred to the soil, and reaction is the load which is soil imposing towards the structure. Okay. Now, for determining the soil pressure, you have to calculate QU, which is equals to load divided by the area. Load here is used as a factored load. Therefore, obviously, the factor of safety is 1.5 for load. It is 1.5 times of P divided by the area of the footing. Okay. The next thing is calculating the depth of the footing. Basically, the depth of the footing is calculated as per three design considerations. One is as per the consideration of bending moment. Second, as per the consideration of single shear, and as per the consideration of double shear. Now, first of all, will be studying from the consideration of bending moment. For bending moment, the maximum bending moment is considered to be at section XX or at the edge of the column. Okay. First of all, let's understand the projection of footing, or this L, or the distance of this section XX from the face of the footing. Okay, and this L is nothing but total width of the footing minus the width of the column and half of this capital B minus small b, since we are using the half of the section. Okay, now this is L, or the projection of the footing. As we all know, the soil pressure is QU. The soil reaction is QU. So Q, calculating the moment at the section XX will be QU into the distance L, or the projection of the footing, which is B minus B by 2, into half of the distance of B minus B by 2. Okay, so it is going to be QU into P minus B upon 2 whole square. Now B minus B upon 2 is nothing but the projection of the footing, that is L. Therefore, we can say that the bending moment is QU L square by 2. And if you remember that bending moment for a cantilever section is considered to be WL square by 2. So this part is considered as a cantilever. Okay. Now this minimum depth required is obtained by treating the above equation as limiting moment. Okay, so we know for the type of steel, based on the type of steel, that is whether being mild steel or Fe415 steel or Fe500 steel, we have these three equations for the limiting moment. Okay, using 0.148 Vd square FCK for mild steel, 0.138 Vd square FCK for Fe415 steel, and 0.133 Vd square FCK for Fe500 steel. Moving forward, now let's see the consideration of one-way shear. As per the beam theory, the critical section is at a distance d from the face of the column. At distance d from the face of the column. Yeah. You have to calculate the shear force. Therefore, the design shear, or VU, or we can say that the pressure that soil is exerting from the shaded area. If QU is the soil reaction, QU into B, that is the width of the footing, into this width of the strip, which is capital B minus B by 2 minus D. I'm telling once again, we have to calculate the shear force at this strip. This is this shaded area. Okay. This shaded area having soil reaction as QU into B into the width of the strip, which is B minus B by 2 minus D. Since we know that B minus B by 2 is the distance from the face of the column. Okay. Then the next thing is you have to calculate tau V, which is obviously VU by VD. Tau V is not greater than or equal to tau C. And tau C is nothing but the critical shear stress in concrete. So the minimum depth required from the consideration of one-way shear is equating tau C BD to the soil pressure from the shaded area. Okay. So the depth comes out to be D is equals to QU upon tau C plus QU into B minus B by 2. Now you have to remember one thing. You don't have the value of tau C here. So the minimum value of tau C that can be used is 0.2% of the steel. Okay. So since we are not given SP16 in examinations, so you have to use IS 456, and for that you can use, you can obtain the value by interpolating between the values corresponding to the percentage of steel of 0.15 to 0.25. Next is from the consideration of two-way shear. Two-way shear is also called as punching shear. Basically what happens, this column has a punching effect on the footing. That means column is going to suppress the footing and from a distance of d by 2 from the face of the column. Therefore, IS 456 recommends that the critical section for punching shear is at a distance of d by 2 from the column. Okay. The perimeter for this punching shear area is 4 times of B plus D. How is it coming? B plus D by 2 plus D by 2. So it is coming to be B plus D on all the four sides. Okay. Now area of this resisting punching shear will be the perimeter into the uh, D. Okay. The force punching shear force of punching S is given by QU into the shaded area. Okay. QU is the soil reaction obviously into the this shaded area, which is at a distance of d by 2 from the face of the column. So this is coming out to be QU into B square minus B plus D whole square. Okay, when you will be calculating the area of the shaded area, this comes out to be B square minus B plus D whole square. यानी कि total area of this footing minus total area of this dotted rectangle, dotted square. Okay. The punching shear stress tau P is given by S by A, where S is what? S is the punching force and area, and A is obviously the area of concrete resisting this punching force. Okay. Now, the permissible value of tau P is 0.25 times under root of FCK. Now, since you will have FCK in the question, you'll be easily able to help. You'll be easily able to calculate tau P. For footings with uniform thickness, usually one-way shear governs the depth, and the other two cases may be used for checking the depth selected. Moving forward, the next step is to calculate the area of reinforcement required in width B using the expression mu is equals to 0.87 Fy into AST into D into 1 minus AST upon V2 into Fy upon FCK. Using the dia bars not less than 10 mm, determine the spacing of the bars and provide the reinforcement in both the directions. Now the next step is to calculate the bond length, which is LD is equals to 0.87 Fy upon phi upon 4 tau B. We are well aware of this formula since we have already studied the min slabs. And the last step will be the sketching of the sketching with the reinforcement details. Now moving forward, we will be solving an example for understanding the design of a square footing. Now the question is, you have to design a square footing for a short axially loaded column of size 300 mm by 300 mm carrying 600 kilonewton load, and you have to use N20 grade concrete and Fe415 steel. Safe bearing capacity of the soil is 180 kilonewton per mm square, per meter square, and obviously you need to sketch the details of the reinforcement. So as we've already seen that the first step will be determining the size of the footing. Okay. Now load that is being um, given in the question is 600 kilonewton. So P is obviously 600 kilonewton. You have to consider the self weight, that is 10%. Therefore, the self weight will be coming out to be 60 kilonewton, and therefore the total load will be 660 kilonewton. Safe bearing capacity is again given in the question, which is 180 kilonewton per meter square. So the area of the footing, capital A, is equals to 1.1 times of P divided by safe bearing capacity. That is, total load is 660 divided by 180, which is coming out to be 3.667 meters square. And obviously, since it is a square footing, so the size of the footing will be under root of the area, which is coming out to be 1.91 mm. And as I mentioned earlier, that you have to uh, round it off the higher end of the 100 mm. So the thing will be that you have to provide a square footing of 2 meter by 2 meter. The next step is soil reaction for the factored load. You have to calculate QU, which is given by the formula 1.5 times of P divided by the area. So it comes out to be 0.225 Newton per mm square. The next step is calculating the depth. Okay. Now from the consideration of shear, depth will be found and checked for two-way shear and bending. Okay. The soil pressure for the shaded area will be, as we have discussed earlier, uh, it's VU, that is equals to QU into B multiplied by B minus B by 2 minus D. This figure will help you understand it better. So you have to calculate uh, the soil pressure for this shaded area. Okay. So 0.225 is the soil reaction. QU into B, that is the width of the footing, sorry, width of the footing into the width of the strip, which is what? B minus B by 2 minus D, that is 2000 minus 300 divided by 2 minus D. Okay. Now, since we don't have the value of D, obviously we have to calculate that value of D, which is nothing but the depth of the footing. Therefore, the minimum depth comes out to be, you have to equate 450 into 850 minus D to 0.32 into 2000 times of D, and therefore the D comes out to be 351 mm. So rounding it off, you have to provide a minimum effective depth of the footing as 360 mm. Now we have calculated the depth and we'll be checking it for bending and for two issue. Okay. For the check of the bending, since it is given that you have to use N20 grade of concrete, therefore MU limiting for N20 grade of concrete is 0.138 BD square FCK. So the bending moment will be the limiting moment will be 715.39 into 10 to the power 6 Newton mm. And you have to calculate the bending moment at the face of the column as shown in figure 9.11. You have to use the formula which I have explained earlier, QU into capital B minus B whole square divided by 8. So the bending moment comes out to be 162.563 into 10 to the power 6 Newton mm, which is obviously less than MU limiting. So the depth provided is sufficient. There's no issue. Okay. For check of two-way shear, that is for punching shear, you have to consider the critical section, which is what? At a distance of D by 2 from the face of the column. Mind it, this small d is nothing but the effective depth. of the footing. Okay, the perimeter of the critical section is 4 into 300 plus 360, that is 2640 mm. Area of the critical section is again perimeter into the into D, that is 2640 into 360. Now, as we know that two-way shear is equals to upward pressure in the shaded area divided by the area of critical section, which is two-way shear is, that is tau p, as I had said. Therefore, tau p is nothing but the uh, 0.844 Newton per mm square. This two-way shear, as I said, that it is called as punching shear. Therefore, tau p is nothing but the punching shear, which is coming out to be 0.844 Newton per mm square. And the maximum permissible punching shear is 0.25 under root FCK. Therefore, it is 0.844 Newton per mm square. Therefore, whatever depth you have taken, that is 360 mm, is sufficient from the consideration of two-way shear. Okay. Now the next step was calculating the area of steel. Uh, since the moment is 162.563 into 10 to the power 6 Newton mm over the width of 2000 mm, therefore the area of steel comes out to be 1299 mm square. You'll be getting this quadratic equation. After solving this quadratic equation, you'll be getting the area of steel as 1299 meters square. Since we have calculated the area of steel, now the next step is to provide the spacing, which comes out to be 174 mm center to center. Sorry, 174 mm. Uh, Now, what you can, since the minimum dia bar that can be used as 10 mm, we are providing here 12 mm dia bars at 170 mm center to center. Now, the percentage of steel that is provided is 0.185. As per the percentage of steel, the tau C is 0.308. Using table 19 of IS 456 and interpolating the values, the next step is tau V. Um, as I said, using equation 1 and 2, tau V is equals to V upon Vd, which is 0.306 Newton per mm square and less than tau C, hence the design is okay. And the last step is development length. Calculating the development length with the help of this formula of LD, that is 0.87 Fy into phi upon 4 tau Bd, and tau Bd is 1.92. Using the clause 26.2.1.1 in IS 456, LD comes out to be 564 mm. Okay. Now this 564 mm is available beyond column face. Hence the design is okay, and this will be an approximate design sketch for the reinforcement details. With this, I wind up my lecture. Thank you very much for listening so patiently.